Parachute in the wind. So this is in still air, a parachute would fall vertically at a terminal speed of 40 meters per second. So you guys know that when you drop, when you jumped off a building last night, when you jump off of something, at some point the upward force due to the air resistance is going to equal your downward weight. So that's going to be your terminal velocity at that, because it actually depends on the velocity, the square of the velocity. But like for an ant, the terminal velocity is so small, that's why it can drop from such a high height and not die when it hits the ground. We can't do the same thing. So this one's all about the terminal velocity of a parachute would be 40 meters per second in still air. Find the direction and magnitude of its terminal velocity relative to the ground if it falls, and a steady wind blowing horizontally from west to east. All right, so it's dropping down 40 meters per second. We have a wind blowing from west to east at 10 meters per second. So how do you think, now this is kind of nifty, where would you draw the resultant vector? I mean, how is it at, what's the motion of this thing actually going to do then? Yeah, exactly. It's just that these are all black, just trying to pretend. Alright, so I've got this here, will be how it actually goes. And that's what they're asking for, is how long is it and what's the direction? So you can give me an angle relative to due down or whatever, right? So really this is just right triangle geometry, trigonometry. So how do you find that length? And actually, how do you do it vector-wise? Let's try to do it vector-wise. What will the vector notation for this be? What's the vector notation for this one here? U. I like U. Now, be a little more specific. And how do we want to define, and it's really up to you, how do you want to define down, up, east, west, right? So it's falling down, and we have this wind blowing. Okay, cool. And which way, in general, do you want to call it down, comma, east, west? Right? East. Down, comma, east, like. So we'll say those are our two positive things. And if you think about it, if I chose a different way to define this, all that means is the negatives would indicate the other direction, but who cares? When I find the distance, don't I square them all anyway? Right? And the angle would just be relative to either down or relative to east or west, right? So it's still the same idea. You still identify, but you have to tell me kind of like how you want to describe vectors in this problem, right? Is everybody kind of with me? How would you describe this vector? What would this vector then be? And so like we're defining down to be positive and east to be positive. So if it was going up and west, it would be negative, negative. So this would be 40, comma, 0. Because it's going down 40 and it's in still air, it's not going east or west at all. How are we doing so far? So you don't have to do it exactly like that. You can pick up to be positive. If I want to pick down to be positive, why? Because it's going down. I don't want to bring negatives in if I don't have to. And then what's this guy? Yeah, exactly. He's not going up or down. That wind is purely blowing to the east. So that's a beautiful vector addition problem. What's the resultant then in vector speak?
40-10.
Yeah, 40-10. So now your whole problem now is what's the length of that? What's the magnitude of that? And it goes right along with what you would do if I just asked you to find this last side of the triangle. Right? The work is the same thing. So what would the magnitude of that be officially? What's the magnitude of W?
Radical 17.
Radical 40 squared plus 10 squared. Yeah. Blah, blah, blah. Whatever the hell that is. Just a little more than 40. Right? And what about the direction? How would you find the angle?
And the tangent of 10 over 40. About 14.036.
So where's that angle in our picture actually? Which gets a little bit interesting. Where would that angle be in our picture? And so this is where you could be a little more precise. You could say, so right now, this angle is going to be, and since it's based on tangent, isn't that angle going to have to be there? Right? Actually, the way you gave it to me, 10 over 40, so you actually did it right. You put it up here. Cool.
Yeah.
I like it. Sorry. I was making an assumption that we would end up in the wrong place. I love it. So to get it up there, she didn't do 40 over 10. She did 10 over 40. Makes that the angle. That's where the angle is. Are you guys with me? I mean, if I did inverse tangent of 40 over 10.
That is the reference angle.
Yeah, well, that would be in the wrong place, right? So I want to do the inverse tangent of 10 over 40. That puts it right there. And then I can describe it in terms of degrees away from straight down, right? So I could say, for example, so what do you guys get? What's the inverse tangent of?
14.036 degrees southeast.
Is that what you got? 14.036?
036.
Okay, right. It's not south in this and all, right? It's a little bit weird. They're using east and west and up and down, which is a little strange. So I would say 14.036 degrees east of down. Cool. And that's just bringing into the fact that we got east-west, we got north-south. That would be two-dimensional analysis. We're just bringing in the third dimension, right? So how many dimensions are involved in this problem? Two. Now when I say we're bringing a third dimension, we're bringing in the dimension we normally don't think of when we think east, west, north, south. We don't think up and down, right? We don't think topologically normally, even though now Google is getting more and more. But before, you just look at a map and everything's flat. Where am I? I'm here. Where am I? Where's the other guy? Here. We're close. No. You're in a freaking mountain. You're really far away. You forgot the z-axis, right? You guys kind of with me a little bit. Okay. Somewhat. Okay. So that's how I'd say it. So here at the end, I'd say east of down, which sounds like a band name. We are 14 degrees east of town. Maybe it doesn't sound right. Any other questions? Oh, there was a, what was the other one? 74? I like it. So this one is, for those of you who've done any physics, this looks painfully familiar. A block on the inclined plane. You do this until you go crazy. You do it first with no friction, and then people go, oh yeah, friction. Friction. So you do it with friction. And then you got stuff hanging over the sides, and you got, this part is frictionless, and you're like, where do I buy that wood? You know, I like those parts. It's a massless string, really. So I've got this, what's it tell me here? I got to find these components of this force here. So they want the components that are perpendicular and parallel to the surface of that inclined plane, right? And that only makes sense because the force in this direction obviously is what's going to make it move. The force in this direction is what increases or decreases its friction, right? So if this force is not big enough to overcome the friction made by that, then I have to make it go up a little bit if I can to get it to start moving. So those of you who had physics, that sounds very familiar. If you haven't, hopefully that just makes sense, right? So they give me, what do they give me here? They give me 30-degree angle. It's a 100-kilogram block. They give me a 30-degree angle here. So what would this direction be dependent on? And in these problems, you can do it without writing anything vector-wise. And I don't blame you if you do that. In fact, at this point, it's fine to do that just to get you remember all the trig and stuff involved. This is a little tricky because the angle is there. It doesn't immediately have anything to do with this. And the way that I always remember this is if I go to an extreme, if I put the inclined plane all the way down, this force should be what should be true about the force going down the plane if I put the plane all the way down on the floor? Zero, right? So which trig function goes to 0 if I take the angle to 0? Sine of 0 is 0, right? So this has got to be the sine piece. And this has got to be the cosine piece. Because at 0, this is going to be maximal. If you take it to its other extreme, 90 degrees, right, if you can get that up there, then everything's down. There's nothing going into the wall then, right? Okay, all right. It's another group of kids I don't want to play poker with, All right, so this isn't too bad. This is about breaking it up into components. You could originally write everything component-wise, but now we get a little bit freaky because we haven't talked it. Today we're going to look at the same kind of problem in a different way using multiplication type operators on vectors. But for right now, it really is just breaking it down into components. Cool. Remember what I said? Were you ever told this that sine and cosine are like percentages that go in that direction? Do you know what I mean? Like sine is the percentage that's in the y direction, cosine is the percentage that's in the x direction. If you think about it like that, it makes a lot of things a lot clearer, right? It explains why sine and cosine are between 0 and 1. The negatives just tell you direction, right? 100% at most, so forth. So to finish this out, what's this component? We'll call this, what do you want to call that piece? F. We'll call it Fs for the sine piece. And this is normally the normal force, but we'll call it Fc for the cosine piece. What's Fs going to be?
It's 98 times sine 30, because you have to do gravity times the kilogram, find the force.
Where are we at?
It'll be just the weight.
Yeah, okay, cool. All right. So this would be mg, the weight, which would be 100 times 9.8. 980. Very good job. So the force down in this direction would be what?
98 sine 30.
So this, everybody cool with the fact that this is the sine piece to go down. So I want this percentage of that force going in that direction. So this 980 times sine 30. Cool. And what about the other piece of force? 980 cosine 30. Yeah. Now, real quick, if you like this better, what sucks about this angle is it's not directly in any triangle I made up here, right? So you could try to work that angle into play up here. In fact, what's this angle got to be here? 30 degrees. So you can try to work it up there and then try to draw a triangle out, and you'll end up with these. I mean, that's another way to go with this. To me, it just makes more sense to stop and think, which does it make sense? Which cosine or sine makes sense here? It's got to be sine, because in the extreme case, it's got to go to 0. Or in this extreme case, it's got to go to 100%. All of it. Right? So in those inclined plane problems, it's always going to be the sine piece going down, the cosine piece going directly in, perpendicular to the surface.
Can't we say this force is going to be perpendicular to the normal force, so we know that's 90 degrees, therefore that's 30 degrees, and we got this 60.
Yeah, exactly. That's what I'm saying. You can work that 30 degrees back into however you want to draw your triangle. Exactly. If you want to do it that way. Cool. I like it. Obviously, these have got to be perpendicular because one of them is parallel to a plane, the other is perpendicular to the plane. Therefore, they have to be perpendicular. Yeah. Cool. All right. All right. Any other questions from the first few sections in 11? Yeah.
It's 1.2, 62.
Oh, yeah. Cool. It's page 702. So 500-pound load hangs from 4 cables of equal length that are anchored. Let's see if we can do this. It's not terrible. It's not good. Those points. Okay, neato. Okay. stay away from trying to draw that. The coordinate system on there, I had enough trouble with my cables. The load is located at 0, 0, -4. Find the vectors describing the forces on the cables due to the load. Cool. And they tell you it's 500 pounds. Blah, 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 blah. Okay, cool. So they want actual vectors on this one, right? So you can start it off the same kind of way we did there, trying to find the components for each one. So, what did you try so far? Who asked that question?
I said, I kind of tried to do the distance in between the connection point and over there.
Okay.
Um,
Because what is it for the vectors that you need? What two pieces do you need to fully put together a vector?
I need X, Y, Z,
Magnitude
magnitude,
and direction. I like it. Cool. You can break it down to its components, but that will have inherent in it a magnitude and a direction. So if you can get the magnitude, and normally we get magnitude like we did here, or like we did earlier with just putting the Y and X pieces back together. And you can get direction by looking at the triangles that you create. That's one way to do it, right? So what else did you try? So
I did the magnitude is equal to 4.
now what do you think
Well, first I did, because we have only points, so I created a vector of that, and then I calculated the magnitude.
So with these points,
Because we have also.
okay, cool.
points.
So you have points here and here. You know this is at 0, 0, -4. Oh, that's right. I kind of drew this horribly.
So in the middle.
Oh boy, I made an assumption before I looked at the picture. All right, so they're all connected at that point. There, cool. So you know this vector here, and that vector, and so forth. So what's that vector there?
It was 0, -2, -4.
And which direction do you think that vector should really point?
So 0 in X direction goes.
And really, this is if this force is pointing down, then the forces supplied by these would be pointing up, right? So I don't know if they really make a distinction. No, they say find the vectors showing the forces in the cables due to load. So yeah, I'd say down for this because that's what's pulling on it, right? So if you've taken any physics, you know about the counteracting force to keep it from falling. But here they're just talking about what force does the rope actually experience? How much is it pulling on it? Okay, so the big thing about these is which direction on each of these ropes, what direction is the force acting in? I mean, what part of the rope actually works to counteract this weight? Which component of each of the ropes? So for example, if I have a box in between us and you've got one rope and I've got the other rope and we're carrying it between us and it's connected to the middle,
Negative Z.
only the part that's in that same direction is going to be able to counteract it, right? So all of these upward components, let me just look at this one right here since it's a little easier for me to draw on. I've got this component of it and I've got this component of it. All of these have to add up to be what? Of course, it's a little harder for me here, but let me see if I can do it. All right. Here's my little right angle here. Okay. Oops. How am I drawing? Oh, the map. So these sides of this have to add up to be 500. And the way they've made this, they made it a little bit easier on us because of the fact that they're all the same distance away, right? How far away is each one of these points from that? You just have to do it once.
I did a 4 for 4. 4?
Yeah, because for the distance for any of these, it'll be the square root of 16 plus 4, right? For each of those, how far apart they are? Well,
I calculated 4.
how'd you do? So like for this guy, what's the actual vector for this guy? What's this guy, the vector?
Yeah, it's 0, 2, -4.
0, 2, -4. Okay. And of course, his magnitude is going to be the square root of 4 plus 16. Cool, okay. So the magnitude of that one is square root of 4 plus 16, square root of 20. But what I want you to realize is you're trying to piece together the forces that are on each of these ropes. How much force is on this rope here? How much force is on this piece of this rope here? If they got a hold of 500 pounds,
So it's some fraction of that? So it's going to be
Is it going to be 500 divided by 4?
since they're all equally spaced, they're all equidistant from the center, none of them are holding up more than the other one, right? So you can imagine if I'm holding something and you're helping me out by pulling on a rope, we're not holding the same amount of force. We're not contributing the same carrying force, right?
divided by 4 then?
Yeah.
How many ropes is that? 5?
So there's one triangle here.
No, because you're adding
Just taking this triangle here and there. So you guys might start to realize what I really need to know here. This is going to be 500 divided by 4, just to hold that thing up. So that's 125. Cool. So what do I really need to know about this to finish breaking it out into components?
Angle, direction?
Yeah, and the angle you can figure out.
Is it 36 to 90 triangle?
Why would it be that?
I would say it's
So look at the triangle again. That's the force, right? That's the force. Look at the distance here. And again, we see a lot of problems with triangles where you can get angles. You can look at it as distance. You can look at it as force. Because it's going to have to be the same triangle. It's going to have the same angle. So this side is how tall? And how far is this side? Yeah, so this side is going to have to be 4. Because it's got to go down to this. And this side's going to be how far? 2. Cool. So this will be 2. This will be 4.
but how is it 125?
That's the force.
That's the force. I love it. So do you see how we have two different ideas on the same triangle? And you see this kind of problem a lot. Right now I can't exactly remember which level you start to see this kind of problem at, but I think it's pretty early. You could have a triangle where you talk about the speeds and you talk about the distance after so much time, and of course those should set up the same triangle. They should have the same angles in that, right? So what, can you figure out the angle here? Yeah, you can take the inverse tangent, 4/2, right? So this is one way to do this.
It's more than it's 63.4.
Okay. Cool. Whatever that is. Blah, blah, blah. What am I still missing to get this in vector form? I've already got every single one of these has, I've already know one component of their vector form. Every single one of these. I just got to be careful with the sign that I use, positive or negative. Every single one of these little triangles I've drawn, what do we already know about it? I keep drawing this the wrong way, but hopefully you're right. This side is going to be 125 pounds, right? So I know every single one of these have a vector that looks like yeah, this is going to be straight down, 125 straight down. So this last piece is going to be 125 negative. So that much we know already, right? All we're trying to figure out now is, for example, for this triangle, what's this last side going to be?
If we know angle, we can use 125 times the sine of the angle. Well, there's a relate, we can use sine.
So now think about it. I kind of gave it away. did we really need to do this? If the angle's always the same, and what are sines and cosines and tangents really? At the base of them, what is a sine, what is a cosine, what is a tangent? What are they? It's really stupid when you think about it. What is a sine, a cosine, tangent? What's their fundamental definition? What's the tangent, what's the sine defined to be for a triangle?
Opposite.
I love it. So they're each ratios of sides, right? Does that make sense?
Mm-hmm.
So if this is 2, 4 here, what's another way to figure this out without having to go through the angle?
Like you would put sine of 30th and then 4 over whatever is missing. What's your question?
Without using angle?
Yeah, without using angles. Because if angles are just ratio, if trig functions are just ratios of sides, cool? And you already know one side in terms of poundage.
Mm-hmm.
Yeah.
Since the distance going upward is double the going across, we should just divide by 2.
Yeah. I mean, if this is 2, 4, and then I said, well, what 8 would it be? 4, 8, right? If this is 2, 4, this is what 125? Half of that. And you would get the same thing if you went through this, because inside this is those ratios. It has those ratios in it. But there's a more direct way to get it.
62.5.
Okay, yeah. Cool. Tie my shoe real quick. Somebody look at this problem again. Blah, blah, blah. Yeah. I like it. Cool. So now the only thing you have to be careful about, so what do we know now? We know that this guy, which direction is that? Where am I going to put that component in its vector form? And I kind of drew this. I want to focus on this guy, right? I know this is 125. We know that just so it can hold this bad boy up. What we didn't know was what this was.
So it's
in the middle.
Yeah, so now we know that it's 62.5. Where's it going to go?
The Y.
And you can look at their coordinate system in there again, but it's got to be along that y-axis for that. Right, so this will be 0, 62.5. At the end of the day, what's going to happen when you add up these vectors that you get? If you add up all the vectors you're about to get, what should happen?
They're going to equal 0.
So if I add this one up to this one, so this could be like 1, 2, 3, 4, is that cool? However you want to say it on your paper. So V1 is this triangle right here. If I add that to V2 to V3 to V4, let me see if you guys can get this. The answer better be what? 0, 0, 500. Right? In fact, negative 500 really, just to show that there's a negative 500 pound load on there, right? And it only makes sense what's going to happen back here when you do this one. It's going to be the same triangle, except this is going to point in the negative x-axis direction, right?
It's going to cancel with going positive.
Exactly. So like this one's going to cancel, I'm sorry, where am I at? This one's going to cancel with that one. My picture's really terrible.
Yeah, all the Y's are going down.
This is going to, yeah, there's the x-axis. This is going to cancel with that one. This is going to cancel with that one, of course. Cool, maybe. But that's the cool thing about, off the top of my head I can't come up with a problem like this, but you see a lot of problems where there's distances involved and then there's something else on top of that, but the ratios have to be the same. It's the same triangle, the ratios have to be the same. Okay, maybe. Yeah. Oh, sorry.
Okay, let him ask.
Jeff, the answer, because I tried to do like the problem 61 and the odd one, the answer there, they have some scalar multiple. Is it because they factor out from this vector number?
You have, that one's a little bit harder because that's got a couple of vectors that have 2 components going on. So we can't make it quite as easy as we did. I just had to look at a triangle for this, right? For that one, you're going to have stuff having 3 directions. Here, I only had to worry about 2 directions at once. There, I've got position vectors that already have two components to them in the x and y direction. And of course it's got that weight. So it's got all three to worry about at once. So that's why 61 is going to be harder, really, yeah. So if you could do 61, and you've got the answers to kind of back you up, 62 you could do it the same way, and hopefully you get the same answer, but it's a lot quicker if you just realize it's just two dimensions I'm working with, not all three in this case. Each one of these have only two dimensions involved. It's been offset by one direction and it's being pulled down. It's only two directions involved, two dimensions. Yeah. Cool. Those application problems, I think, are always going to be the hardest, obviously, because they don't just give you a problem. You got to set the problem up yourself based on what they give you. How many guys, remind me, how many guys have already had some physics? Oh, more than I think originally said. How many have physics in your future? Okay. Oh, some of the same hands going up. More physics coming for you guys. All right. So if you've had physics before, this should sound vaguely familiar. You probably didn't have as much vectors involved. But a lot of stuff is the same idea, breaking it down into parts and going from there. Any other questions from 11.1, 11.2? Did you have a...
No, I was just going to say, like, the way I looked at it is I said the force is equal to, well, because it's a vector, the magnitude times the direction. All I did is I found the direction, which is a vector, by adding up all these four vectors, and I got 0, 0, negative 16. And then...
No, wait, let me catch up to you.
Okay, the vector, if you take, what I did is I took 4 points and you have a fifth point. So I found 4 vectors connecting.
Oh, good. So you found all 4 vectors.
Yeah. And I added them all together, and I got 0, 0, negative 16, which is just a scalar, it's just times 4 of that vector. And then I just found the magnitude, because well, if you times x times those directions, it gives you negative 15. And then I just found x, and I took that and
I
multiplied.
like it. So you sort of did something we're going to talk a little bit about today, which is a more direct way to do this kind of problem, which I love. Yeah, there's more than one way to do each of these problems, really. And there are ways you can do it entirely using vectors. There are ways you can do it not using any vectors. Yeah. So today we're going to learn a couple of really useful multiplication methods for vectors. And one of them sounds like what you were doing there, which I like. That's cool. Any other questions from 11.1, 11.2? Not yet. Okay. And really, you would expect in 11.1 and 11.2, you expect to use the idea of adding components or finding components, and then putting them in the right format, right? So that's exactly the kind of problem you saw there. Putting the right components together, and then at the end putting it in the right format, making things go in the right place. Okay. I think last time there was one last thing in section 11.2 I wanted to talk about. Yes, cool. Can somebody remind me in 2D? I think I've already asked you guys this. What's the equation of a circle? General equation of a circle. See?
Y squared plus y squared.
So there's like the nice unit circle centered at the origin. So in general, you can have a circle like this here. So that would be a circle centered at AB with radius R. Cool. So if I extend this to 3 dimensions, what type of shape am I talking about, of course? Sphere. And the really beautiful thing is, does everybody here know where the equation of a circle comes from?
An integral.
So a very quick thing about that. Not an integral yet. Integrals would be going from surface area to volume, right? That's what those are good for. If I have a circle centered at, let's start off with just centered at the origin. And then you can just use translations to go centered at whatever the hell. If I have a circle centered at the origin, and I've got some point on it, x, y, And this is a really cool thing I think about geometric shapes and their corresponding equations. If you can figure out the basic definition of the shape, you put that into math, and there's the equation. So what do I mean by that? What's the basic definition of a circle? A circle is a collection of points that do what?
They all are the same distance from the origin.
I love it. So they all have the same distance, in this case, from the origin. And I don't care about the other case, because once I figure this out, I can just translate the damn thing around. Who cares about the A and B yet? Right? So if they have the same distance, well, here's the origin. What's the distance? The distance has to be the same for them all. We're going to call it R. And that's the square root of x squared plus y squared. So r squared equals x squared plus y squared. Bam! And then you can translate it all day long. Right? So is the distance formula fundamentally different in 3 dimensions? No, it's just x is squared, y squared, and z squared. You just throw the z's in there, right? It's the same stupid idea. And in fact, whatever dimension you want, it's the same stupid idea. So should the formula for a sphere be fundamentally different from the formula for a circle? Because they're both based on distance. No. So a sphere formula would be x minus a squared plus y minus b squared plus z minus c squared equals r squared. Right, so this is a sphere, a hollow thing. We're only concerned with the points that are actually on the surface of the sphere. The other possibility would be a ball. Right? So in a case of a ball, I want to catch all the points on the surface plus all the points inside, right? So when it equals r squared, I have to be that far away. Well, if I want to catch all the points that could be closer, I just make it less than or equal to. Right? So this would be a ball. Less than or equal to r squared. Right? And then you get into, what about an open ball, where that's when you get further down, where you don't want to include the stuff on the surface. And then you just make it strictly less than. Ooh. Right? That becomes big way later. So that was the last little piece of section 11.2 I had to talk about. Make sure you guys remembered. If you remember that circle, you're good with spheres and balls. Right? So really what I want to focus on today is talking about 2 types of multiplication. So we already talked about how vectors add. We talked about how vectors subtract. What we have yet to talk about is how they multiply. Right? And then division is its own thing. Don't worry about that. Vector multiplication. Oh, you guys all, real quick before I forget, everybody got my email about student solution manual? I tried to piece together from what I could get a student solution manual for 11.1 and 11.2. They'll have some in the bookstore. You can order it directly. It's going to be the same price in the bookstore as it would be online, come to find out. So they should have it in the bookstore by tomorrow. Has anybody looked yet? No? Okay. So you're all not, yeah.
It's the new book, Student Solution Manual.
Exactly. The one for this book. Yeah. And actually it's going to be specifically for, they should have it, it's going to be like $37, I think it said it was, just for, I think it's chapters 8 through 14 actually. So it'll encompass us.
They have it for 30 online, so I guess it's
They have the...
on Amazon has it for 30.
Oh, for 30? Oh, okay. So, okay, cool. And so you can order it through there. Wherever you can get it, it's great. These get a little bit tricky. Let me give you a nice physical example to work with first. If I was going to, let's say I had a box sitting next to a, for some reason next to a cliff. I don't like it there. I want it moved away from the cliff, right? It's a really heavy box. Don't get in all the specifics. It's it's some weird Super Mario Brothers thing or whatever, if that helps. So I need you to move this box, and I'm going to pay you. Let's just make this a little easier to look at. I'm not going to worry too much about it. I'm going to pay you money for moving it in this direction. I'm going to pay you, like $8 per foot that you move it in that direction. It's a heavy damn box. But you notice that going this way, the ground is rough as hell. Right? And you notice, oh, there's like a groove in that direction. I'd rather go that way. You're not going to get money for the feet that how long that is, will you? I mean, I was very specific. You got to make sure that if your employer is a calculus teacher, you got to be careful about the way he says things. I'm going to pay you $8 a foot for going in this direction. How much in that direction did you go? Let's say you make a 60-degree angle here, right? And you go 10 feet. Is everybody with me? Mm-hmm. How much of that 10 feet will I actually pay you money for? So how much money? You won't get 10 times 8. Yeah, so you'll get, how far did you actually go in this direction? What's this component of your motion? What's this? I like it. So this component of your motion would be 10 times sine. Cosine. 60 degrees. Cool? And that, of course, cosine of 60 is 1/2. If you don't know your trig stuff, go back and review it, right? Cosine of 60 is 1/2 times 10 is 5. So how much money will you actually make?
$40.
5 times 8, $40. Okay. Now this is still multiplication. The reason vector multiplication, and I gotta be careful when I say that, because there actually is, there's two different types of ways to multiply. One of them ends up with a scalar answer. So we actually end up calling that scalar multiplication of vectors. And actually there's a better word to use for that. The other type ends up with a vector as an answer. So be careful, when I say vector multiplication, I just mean the types of ways to multiply two vectors. This is definitely just money. There's no direction involved there, right? Even if I threw your money that way, it's still $40. Cool. So this is going to be the scalar multiplication. And what's the real formula that I used to get the answer? I took this vector times sine of this, cosine of that angle, and then multiply that by this vector. And that's the magnitude of that vector. I've got to be careful, right? So there's a vector that points in this direction, and it's got that magnitude. There's a direction, there's your distance that you actually went diagonally. That's the length of that vector times the cosine of the angle in between. Okay, maybe. So what's that in general then? If I have two vectors, V, U. One way to multiply these would be to take the length of U times the length of V times the cosine of the angle in between. Cool. And this is called the dot product. All right, so this is given the symbol U dot V. This is one that's also known as scalar product. Get in there. Okay. Cool. And of course, you can see why they say it that, because it comes up with a scalar at the end. Now, what's kind of sucks about this? Because if I give you two vectors, what then must you somehow do to be able to use this? Find the angle. And is that always necessarily easy? Especially if I'm talking about 3 dimensions or even higher dimensions. You know, screw that. So there's got to be a better way to define this dot product that doesn't depend on the angle. And to do this, what I want, I'm going to need some help from you guys, because I'm talking way too much now. So look at this here. Let me draw this picture. Here we go. You might make it look like a 90. Here's the angle in between. So what I'm going to try to do is I'm going to try to look at the relationships between the sides and the angle and try to work it out so I can solve for that angle, for one thing. In the process, we're actually going to see an easier way to do this product. Right? So let's see what happens. I need your help in this. This is a triangle. Step number 1. What does the law of cosines say for this triangle? So just to remind you guys, let me put in a little bit better language here. Here's A, B, C. Here's the angle between A and B. Does anybody remember the law of cosines for this?
A squared.
We need to find
B
theta.
squared minus 2AB.
I like it. So A squared plus B squared. That would be Pythagorean if that angle was 90. And then the law of cosine says, well, if it's not 90, you need a little cleanup. Minus twice AB cosine of C. Or little c, sorry. Oh, screw it. These are screw it. The angle between the two. So we'll call that theta is fine. Okay, maybe. So that's vaguely sound familiar? So can you guys try to set it up for this? What does it look like for that? Now be careful. What are A, B, and C? What are they physically? Sounds weird, but are they lines? What are they? Scalars. I love it. Now what is V, U, and U minus V? Those are vectors. So to write this in that form, what do you have to actually write using their magnitudes, right? Okay, cool. So which side would correspond with these, and then just try and write it in this form. I like this. Some of you guys are working fevers, and the rest of you are like, I'll wait. So which side acts like C here? Obviously.
U minus
U.
V.
Yeah, U minus V. So we got the magnitude of U minus V, which is like C, squared, equals.
The magnitude of B squared.
I like it. So magnitude of V squared plus the magnitude of U squared minus.
2 times the magnitude.
BU cosine.
I like it. Cool. Now, right now, I could point something out. I kind of wanted to do this to show you a nice physical example, and I'm trying to show you a very mathematical way, a process to get there. So I'm not going to bring in dot product directly yet, but some of you guys can see it. Where's the dot product showing up?
Minus.
Right there. It's like twice the dot product here, right? But right now, let's just pretend like I'm trying to come up with a way, how do I find the angle easily between these two? I'm trying to kind of solve this for theta, right? So now each one of these, believe it or not, we can simplify. Like for this one, and I'm trying to generalize to 3 dimensions here. Okay, so I'm trying to be in total 3D, because it'll work in 2D the same way. So in 3D, what is this? What's the magnitude of that vector? And what does that vector look like? And of course, this is where you guys say, I don't know what the hell that vector looks like, man. It's just V. What the hell do you want from me? But it's 3 dimensions.
X, Y, Z.
And be a little bit, and actually you want to normally go, because otherwise you need like an X, Y, Z, and X1, Y1, Z. So we just do it straight on this. So it'll be V1, V2, V3. So U would be U1, U2, U3. That we won't worry about. We'll write that in terms of U and V separately here in a minute. Okay? So, what then is the magnitude of V squared?
U1 squared plus V2 squared plus V3 squared.
Exactly, right? How you find the magnitude of V? You would take the square root of V1 squared and then squared, so square root goes away. So this is equal to V1 squared plus V2 squared plus V3 squared. What's this guy? And then this we'll leave alone, essentially, right now. And this equals to this ugly mess here, right? Now, what is this really though? Let's go ahead and write this out. I said I wanted to write out in terms of U1s and V1s and such, but so what would U minus V be in terms of U1s and V1s?
U1 minus V1, U2
Exactly.
minus V2.
So now you guys might see where I'm going with this, maybe. This side then you can do the same thing with. It's just going to be a little bit uglier. So what I want you to do right now is to finish this side out. Figure out what this is. Put it here. What is this? What's the magnitude of that? And work it out. Keep going. Simplify it. Aw. It's not bad. And just to remind you guys, given any vector, A, B, C, its magnitude, let's say this is the W vector, its magnitude will be the square root of A squared plus B squared plus C squared. Right? So you have a vector. Here. I'm just asking you to find its magnitude squared, which makes it even better. There's no square root I got to worry about, right?
So it's going to be U1 squared minus 2 U1 V1 plus V1 squared.
Yeah, and so forth, right? You just got to FOIL each of those things out. Right? Aw. So on this side we get, let me write it down here. Right over here. So this is the magnitude of U minus V. It'll be U1 squared plus, sorry, minus 2U1 V1 plus V1 squared. Same thing for U2s and V2s, right? Minus 2U2 V2 plus V2 squared. Same thing for U3 and V3. And notice what really happens nice. What happens is nice. All the terms, all these guys cancel. Right? Both sides. That's nice. So now look what else cancels. Can I divide both sides by -2? So what do I gotta get? The magnitude of U, magnitude of V, cosine equals U1 V1 U2 V2. This is the dot product. This is the another definition of dot product that does not involve angles. And that is really stupid easy to get. Just multiply the corresponding components, right? So I get U1 V1 plus U2 V2 plus U3 V. So this, of course, is the required piece of a math class, that is where something comes from. And now you stand on the shoulders of all that work that we just did and go straight to the answer. All right, so for example, if I give you two vectors, let me see if you guys can do this. I want you to find the angle between -1, 2, 3 and 4, -5, 1. So remember, you can use this here, we know. U V cosine theta equals U1 V1 plus U2 V2 plus U3 V3. if you guys can imagine the work it would take if I just gave you this points before I talk about dot products. Find the angle between this vector in three-dimensional space and this vector in three-dimensional space. Do you think it's easy to find the angle? No. Is it impossible? No. But it's freaking ugly. This is beautiful. It makes it so easy. That's a pretty useful formulation for this. Just make it a part of your everyday life. Thank God the dot product makes so much freaking sense. It's stupid. You just take, what is the dot product going to be? What's negative 1, 2, 3 dotted with 4, negative 5, 1? How do you calculate that number? So what's U dot V? If I give these guys names. Yeah, negative 4, minus 10, plus 3. Right? That's awesome. Okay, maybe. And then I just have to take that number and divide it by the lengths of them, and that's the cosine of the angle. Take the inverse cosine. Whenever you do inverse trig, you got to remember, is it a reference angle being spit out? What's the output of the inverse trig function? And you've had that kind of problem before, way back in the pre-calc. So now to find the angle, I just got to take, what's the length of U? Who's got that? Square root of 14.
Square root of 14?
Square root of 42.
42.
So square root of 5.
And now I just got to take the inverse cosine of that mess.
About 116.97.
Blah, blah, blah. Cool, I like it. So we're going to be going between radians and degrees. Radians is preferred in a lot of mathematics. Here, degrees is actually kind of at least on equal footing because it's a little more everyday-ish for us, right? What I mean by that is, if I say that, you can draw me quickly a picture of it. If I say it's 2.98 radians, we could do it. We have to think about it for a second. Where would that be? It's a little bit before pi, because pi is 3.14. You know, but degrees, we have a picture of that right on the top of our heads. We know what that means. What do you think? I mean, I really want you to consider. I could be really evil and ask you to do this without using dot products. Find the angle between those two. But it is not easy. This is relatively easy. This is silly. You must know both formulations for dot product. It's not that bad to remember, right? You got to know this guy, and you got to go to that guy. That guy's easy. Okay. So what do you think is true then for two vectors that are perpendicular, or also known as orthogonal? What's got to be true about the dot product of two vectors that are orthogonal, that are perpendicular?
Should be equal to 0.
Yeah. Have you guys, have they used the word orthogonal yet? Anywhere? So now, yeah. The book uses it all the time. So orthogonal just means the same thing as perpendicular. Right? So to be perpendicular, let's just use U dot B must be 0 because the only angle that